Welcome to this deep dive. We are really thrilled to have you with us today.
Yeah, definitely. We've got a highly anticipated mission for this session, especially if you've been following along with our source material.
Exactly. We are jumping into Module 6 of the Vibe Code blockchain course. And up until now, you've been exploring all the individual pieces of the Stellar ecosystem,
Right. Things like handling payments, minting custom tokens.
interacting with decentralized exchanges, writing Sorbonne smart contracts, all of those isolated concepts. But today, it is finally time to tie all of those pieces together.
It's a huge shift. Learning the individual mechanics of a blockchain is one step, but understanding how they orchestrate together in a unified user-facing product is a massive milestone. We're moving from theoretical concepts into a tangible architecture.
Because building a decentralized application, or dApp, means you are removing the centralized server from the equation entirely.
Right. And the real architectural shift today is how we manage state. When you aren't storing user accounts in a backend database, your front end essentially becomes a stateless window looking directly into the blockchain.
Which requires a totally different approach, right? To data fetching, security, UI design, everything.
Completely different.
I am so eager to get into this because by the end of this deep dive, you are going to understand how to build a complete deployable dApp from scratch.
And we aren't just coding it line by line in the traditional sense, which is the best part.
Yes. We are using an AI-assisted technique called vibe coding to build a portfolio-ready project. Our specific blueprint for this module is a token dashboard dApp.
A really robust one, too.
It is. It's designed to have 5 core capabilities. Users need to connect a wallet, view their balances for XLM and custom tokens, send XLM to any Stellar address, interact with a deployed Sorbonne counter contract, and view their real-time transaction history.
Achieving all of that functionality, which, by the way, covers both read and write operations on a blockchain network.
Yeah.
Doing all of that in a single development sprint is where the concept of vibe coding becomes your primary leverage point.
Okay, let's unpack this. Vibe coding. What does this workflow actually look like based on our sources?
Well, it essentially involves describing the application architecture you want in plain English to an AI assistant, like Claude Code, for example.
So you describe the specific React components, the custom hooks for state management, the utility functions.
Exactly. You describe the required interactions, and the AI generates the heavy lifting. But that means your job as a developer undergoes a fundamental shift.
You are no longer just memorizing syntax or hunting for missing semicolons.
Right. Your job is to understand the overarching architecture, verify that the AI-generated code is sound, and wire it all together securely. It turns you into an architect and an auditor.
Because if your plain English prompt is vague, the AI might generate code that functions but is fundamentally insecure.
Precisely. To be a competent auditor of blockchain code, you need to deeply understand the tools you are wiring together. And the most critical tool in any decentralized application, the ultimate gatekeeper, really is the wallet.
Which brings us to Freighter.
Yes.
In the Stellar ecosystem, our sources highlight Freighter as the official browser extension wallet. If you are familiar with building on Ethereum, you can think of it as the MetaMask of the Stellar network.
That's a great comparison. It seamlessly supports switching between testnet and mainnet environments.
But if Freighter is managing the security, how do we actually bridge it to our React frontend? Like, what are we prompting the AI to build here?
We prompt the AI to respect the golden rule of decentralized applications.
Which is?
The UI must never, under any circumstances, ask for a user's secret key.
Never, because that would completely defeat the purpose of decentralized trustless security.
Exactly. Freighter solves this by securely storing the user's cryptographic key pairs entirely within the browser extension's sandboxed environment.
The dApp simply talks to Freighter, and Freighter signs the transactions on behalf of the user.
Right. And to bridge that in React, we instruct Claude Code to create a custom hook called useFreighter.
So this hook acts as our communication layer with the extension.
Precisely. The useFreighter hook needs to check if the user actually has the extension installed using the Stellar Freighter API package.
And if it is there,
it provides a connect function to request access from the user, returning their public key. It also needs a disconnect function to sever that tie.
And most importantly, it stores that public key in the component state and backs it up in the browser's local storage.
Yes. That way, if the user accidentally refreshes the page, they don't have to go through the entire connection flow all over again.
Okay, so once we have that public key securely held in our application state, we can start building transactions.
We can.
But as we established, our application can't sign them itself. We have to package them up and hand them over to Freighter. The course outlines a specific utility function for this called sign and submit. But before we break down that workflow, there's an acronym that pops up constantly here, XDR.
Ah, yes, XDR.
Can you clarify what that actually is for us?
Absolutely. XDR stands for External Data Representation. It is Stellar's standardized binary format for transactions.
Okay.
See, when you build a transaction in your web app, it's just a collection of JavaScript objects. But the Stellar network doesn't speak JavaScript.
Right, it needs something universal.
Exactly. It requires a highly efficient standardized binary format so that nodes all over the world running totally different operating systems can parse the data identically.
That makes perfect sense. So our application builds the unsigned transaction using the Stellar SDK, and then the first step of the sign and submit utility is converting that JavaScript object into an XDR string.
Spot on. From there, you send that XDR string directly to Freighter's signed transaction API.
And at this point, the control leaves your application entirely.
Yes. Freighter pops up its own secure window, showing the user exactly what the transaction intends to do and asks for their approval.
If they click approve, Freighter applies their secret key signature and hands you back a signed XDR string.
Then your utility converts that signed XDR back into a transaction object and finally submits it to the Horizon testnet for processing.
Now, the sources include a vital warning for developers during this exact step.
The human element.
Exactly. You have to code for human hesitation. If a user is looking at that Freighter pop-up, gets cold feet, and simply clicks cancel, your app receives a rejection error.
And if you haven't wrapped that workflow in proper error handling, your entire React application could crash.
Which is a nightmare. A silent failure or a crashed UI in a financial application destroys user trust instantly.
It really does. Handling those user-generated rejections gracefully, perhaps, by clearing the loading state and showing a polite transaction canceled message, is the hallmark of a professional dApp.
So, with the wallet connected and the signing workflow mapped out, we need to set up the front-end foundation. For this project, the prompt to Claude Code asks for a standard React and Vite project, styled with Tailwind CSS. It is a very modern, fast development stack.
Very fast.
But our sources point out a notorious stumbling block here for developers working with the Stellar SDK on the front end.
What's fascinating here is a completely invisible trap called the buffer polyfill.
The buffer polyfill.
Yes, it is a perfect example of the growing pains in Web3 development. The Stellar SDK relies heavily on the Node.js buffer API to handle binary data.
Which makes sense given what we just discussed about XDR.
Exactly. All of those XDR conversions require buffer to function. However, modern web browsers do not have the Node.js buffer API built into them. They speak a totally different language for binary data.
So if you just run standard npm install for the SDK and try to spin up your Vite server, the browser throws an immediate error because it has absolutely no idea what buffer means.
It fails on load. This is one of the most frustrating issues developers face when transitioning from backend script writing to front-end dApp architecture.
I can imagine. So how do we fix it?
To fix it, you cannot just rely on the AI to guess the problem. You have to explicitly prompt Claude Code to include a compatibility shim, a buffer polyfill inside your Vite config file.
So that polyfill essentially teaches the web browser how to understand Node.js buffer commands.
Exactly. It bridges the gap between legacy cryptographic libraries and modern web environments.
That is such a crucial piece of architectural knowledge to have in your back pocket.
It saves hours of debugging.
Truly. So with the foundation secure and the polyfill in place, we can start assembling the visual components of the token dashboard. Let's look at this through the lens of the user journey.
Good approach.
If you are a user landing on this dApp, the first thing you need to do is connect your wallet. How is our UI handling that initial handshake?
We use the Wallet Connect component. Visually, it presents a clear Connect Freighter button.
Simple enough.
But once the handshake is successful, we don't want to display their entire 56-character public key on the screen.
Right. It ruins the layout and overwhelms the user.
Exactly. Instead, the component truncates it, showing just the first 6 and the last 6 characters. It provides visual confirmation without all the visual clutter.
Okay, so once I'm connected, I immediately want to see my money. That brings us to the balance display component.
Yes, this component takes that newly connected public key and fires off a fetch request directly to the Horizon server.
Horizon being the API gateway.
Right. It acts as the translator between our front-end application and the raw Stellar blockchain. The component is designed to prominently display the native XLM balance while listing any other custom assets the user holds directly below it.
And the UX details here are highly specified in the prompt. It requires a loading skeleton so the UI doesn't look broken or frozen while the data is fetching from the network.
It also has to gracefully handle an account not found error.
Wait, why would an account not be found if they just connected?
Well, on Stellar, an account doesn't technically exist on the ledger until it is funded with a minimum balance of XLM.
I see.
So if a user connects a brand new empty freighter wallet, Horizon will actually return a 404 error.
Oh, wow.
Yeah. The component needs to catch that and display a helpful message explaining they need to fund their wallet rather than just showing zero balances or an ugly HTTP error code.
That's a great detail.
Furthermore, the component is programmed to refresh this data every 10 seconds.
Perfect. From there, the user might want to move those funds. They navigate to the payment form component. Now, in a Web 2 form, bad input might mean an undelivered email.
Right.
But here, bad input means lost money. The validation rules must be ironclad.
Relying on the blockchain to catch your UI mistakes is a dangerous game. The payment form must strictly validate that the recipient address is a mathematically valid Stellar public key.
On this network, that means verifying it starts with the uppercase letter G and is exactly 56 characters long.
Exactly. The amount field must enforce positive numbers. You obviously cannot send negative XLM. You also have to account for optional transaction memos.
Which many centralized exchanges require for routing deposits, right?
Yes, very common.
So when the user ensures everything is correct and hits submit, the component utilizes that sign and submit utility we discussed earlier.
And while the transaction is pending, the submit button disables itself to prevent accidental double spending.
Smart.
If the transaction confirms successfully, the component provides a direct link to view the immutable record on Stellar Expert, which is the network's block explorer.
That block explorer link is a critical UX touchpoint. It gives the user immediate, verifiable proof that their transaction was permanently recorded.
It builds a lot of trust.
Beyond just sending payments, our dashboard allows the user to interact with a smart contract via the contract interaction component. Specifically, we are talking to a Soroban counter contract.
To achieve this, the component uses Soroban RPC server from the SDK.
Because Soroban has its own distinct RPC or remote procedure call infrastructure separate from Horizon.
Exactly. When the component mounts, it fetches the current counter value directly from the deployed contract state.
And it features an increment button, right?
Yes, which packages a smart contract invocation into a transaction, sends it through the freighter signing flow, and once confirmed, automatically updates the UI to reflect the newly incremented count.
Which naturally leads us to the final major piece of the dashboard, the transaction history component. I really want to pause on this one because the architectural approach is fascinating.
It is a massive upgrade in UX.
How does an app show the last 10 transactions and update them in real time as they happen without forcing you to just sit there and mash the refresh button?
The legacy way to handle this in web development is called polling,
where your application constantly asks the server, are there any new transactions? How about now? How about now?
Exactly. It is incredibly inefficient. The modern solution we employ here relies on server-send events, or SSE.
Because Horizon has a built-in SSE streaming protocol.
It does. Instead of constantly interrogating the server, your application opens a single, persistent connection to Horizon and simply listens.
We prompt Claude to encapsulate this logic within a custom hook called useAccountStream.
Right. And this hook subscribes your dApp directly to real-time account updates on the testnet.
Here is where it is really interesting. Whenever a balance shifts or a sequence number changes on the blockchain, Horizon pushes that event down the open connection instantly.
The component catches that event in real time. It can then trigger a refetch of the updated data, and you can instruct the UI to add a brief CSS animation, smoothly sliding the new transaction row into view.
It creates a seamless, dynamic user experience that just feels alive.
It really does.
But consider the complexity we have just built. We have all these discrete components doing completely different things. One is streaming real-time data from Horizon. One is firing off RPC calls to Soroban. And another is handling the freighter wallet connection.
Right.
How do they all stay coordinated? If the Wallet Connect component secures the public key, how does the payment form know what that key is without us manually passing it down through layers and layers of code?
You avoid that messy code structure, which is often called prompt drilling, through centralized shared state. The prompt heavily specifies the creation of a Stellar context.
In React development, a context provides a way to share data across the entire application tree without having to pass props down manually at every single level.
Right. The stellar context essentially acts as the master truth source for the entire decentralized application.
So, what exactly does it hold?
It holds the current connected public key. It holds a global toggle switch for moving the entire application between the testnet and the mainnet.
Oh, that's incredibly useful.
It also holds the instantiated, ready-to-use connections to both the Horizon server and the Soroban RPC server.
So, by wrapping the top level of our React application in this stellar context, every single component we just discussed is referencing the exact same data.
Exactly. It is also responsible for safely managing our environment configuration.
That includes accessing our specific environment variables, things like Vite network, Vite Horizon URL, and the Vite contract ID using import meta env.
Which keeps sensitive configuration out of the hard-coded logic. With the state securely managed globally, the components can focus entirely on rendering the user interface and handling specific interactions.
Let's paint a picture of how all these technical layers manifest visually in the final layout.
Okay.
We instruct Claude Code to generate a sleek, dark-themed application. At the top, there is a clean navigation bar. If you aren't connected yet, the main view is a hero section explaining the dashboard's value proposition.
Paired with a prominent connect call to action.
Right. Once Freighter authenticates you, the layout elegantly shifts into a responsive two-column grid. On the left side, you have your real-time balances and the Soroban contract interaction panel.
And on the right side, you have the robust payment form.
Exactly. Below that grid, stretching full width across the screen, is your animated transaction history.
And finally, anchored at the bottom, is a footer containing a highly visible testnet warning, ensuring users know they are operating in a sandbox environment.
It is a clean, professional architecture that balances complex blockchain interactions with standard web usability. But building it locally on your machine is only half the battle.
You have to deploy it to the web so the world can actually use it.
The course outlines a few deployment options. Because we built the project using Vite, running the build command generates a highly optimized static dist folder containing all our compiled HTML, CSS, and JavaScript.
Which is very standard.
Right. For traditional Web 2 hosting, deployment is practically frictionless. You can link your repository to Vercel or simply drag and drop that dist folder onto a service like Netlify, and your dApp is live and accessible globally in about 30 seconds.
With 0 servers to configure on your end.
Exactly.
If we connect this to the bigger picture, relying entirely on platforms like Vercel or Netlify means your front end is fundamentally centralized.
Oh, that's a crucial distinction.
The smart contracts might be running on a decentralized blockchain, but the interface your users rely on is sitting on a Web 2 server controlled by a single corporate entity.
So if that company experiences an outage, changes their terms of service, or decides to suspend your account, your user interface disappears from the internet entirely.
Right. To achieve true end-to-end decentralization, the sources introduce deploying to IPFS.
The interplanetary file system. Deploying our static folder there completely changes the hosting paradigm.
It shifts from location-based addressing to content-based addressing.
Can you explain that difference?
Sure. When you deploy your front end to IPFS, often utilizing a pinning service like Pinata to ensure the files remain available, your application is distributed across a massive peer-to-peer network.
Okay.
The files are not referenced by a URL pointing to a specific server in a specific data center. They are referenced by a unique cryptographic hash of their actual content.
Wow. So when you host your front end on IPFS, your dApp becomes essentially undeletable.
Yes.
No single server outage, DNS attack, or corporate entity can ever take the interface down. The Soroban contract is unstoppable on the blockchain ledger, and the React UI is unstoppable on the decentralized web.
It is the ultimate realization of a trustless application.
It really is.
However, deploying unstoppable code carries immense responsibility.
Which brings us to a critical section of our sources, the pre-flight security checklist. Before anyone actually deploys this architecture to production, the course outlines some painful lessons learned by early Web3 developers.
Lessons you do not want to repeat.
Let's look at these checks organically. The first one that really stands out to me is validating user inputs. In Web 2, a bad input means a user gets an annoying red error message on a form.
But in Web 3, as we discussed, bad input can mean permanently lost funds or interacting with a malicious address.
You must catch those errors in the UI layer before they ever reach the wallet.
Because if you pass malformed data to Freighter, you risk confusing the wallet, or worse, tricking the user into signing a transaction they don't understand.
Another major checklist item is ensuring you use the testnet first, coupled with very clear network indicators in the UI.
Developers suffer from tunnel vision. They know they are on the testnet, so they assume the user knows.
But you must visually warn users when they are in a sandbox environment.
Exactly. If you don't, a user might connect their mainnet wallet, attempt to send testnet tokens to an exchange, and panic when the funds don't appear.
Or worse, accidentally authorize a mainnet transaction thinking it was just practice.
Exactly.
The sources also emphasize pinning the contract ID. This seems crucial for preventing phishing attacks.
It is. You must hardcode or strictly control the specific Soroban contract ID your UI interacts with via those environment variables we set up in the context.
You never want to create a UI that allows users to paste in arbitrary contract IDs.
If you do, a bad actor could trick a user into using your legitimate front end to interact with a malicious, wallet-draining smart contract.
Finally, we have to sanitize memo inputs. Stellar is unique because it allows you to attach text memos to transactions, which is heavily used by centralized exchanges to route funds to individual user accounts.
But those memos have strict protocol limits.
Right, they can be a maximum of 28 bytes.
Your UI must enforce that limit. And more importantly, it needs to sanitize the input to ensure there are no hidden control characters or malicious scripts embedded in the text.
Because that could cause unexpected behavior when viewed on a block explorer.
Exactly.
It is incredibly important to internalize those security practices. Our sources actually tease that Module 7 of the course is entirely dedicated to diving deeper into this exact topic: auditing contracts, understanding common network attack vectors, and protecting user funds at scale.
Which is exactly the knowledge you need once you master the architectural build process we covered today.
Let's summarize the incredible journey we just took. We started with a blank canvas. By leveraging plain English vibe coding prompts with Claude Code, we architected a fully styled, globally state-managed, decentralized application.
And we learned the mechanics of securely connecting the freighter wallet,
Interacting with the Stellar blockchain to fetch balances and send payments,
communicating via RPC with Sorbonne smart contracts.
and streaming real-time network data using server-sent events. And we accomplished all of that without ever once requesting or touching a user's secret key.
It's a remarkable synthesis of modern React tools and decentralized network architecture.
Truly.
But this raises an important question. We explored the power of deploying your dApp to IPFS so that no single server or entity can ever take it down.
Right.
But if a decentralized application is permanent and undeletable, what happens when you discover a critical, fund-draining security bug in your user interface?
Oh, wow.
How do you push an emergency update or successfully take down a compromised version of an app that lives forever on the decentralized web?
That is a fascinating and honestly slightly terrifying puzzle to leave you with. Building truly unstoppable applications means you have to rigorously think through what happens when things inevitably go wrong.
You really do.
Thank you so much for joining us on this deep dive into the vibe code architecture. Keep questioning the tools, keep exploring the ledger, and we will see you on the next one.